Every moment, right where you're standing, an invisible ocean of energy churns beneath the fabric of reality itself. This isn't science fiction, it's the quantum vacuum, a seething void that defies everything we know about empty space. Scientists once thought it was just nothing, but today we know this so-called emptiness holds the keys to black holes, dark energy, and perhaps the very fate of the cosmos. Across laboratories worldwide, researchers are uncovering bizarre phenomena where particles blink in and out of existence, where negative energy bends space-time, and where the vacuum itself might hold untapped power sources beyond our wildest dreams. In this exploration, we'll dive into 30 of the most astonishing quantum vacuum mysteries from Puzzling Lab, results that rewrite physics textbooks to mind-bending cosmic implications that could change how we see the universe. Buckle up, because the emptiest places in existence are about to reveal their deepest secrets. Imagine tossing a stone into a perfectly still pond. You'd expect ripples, right? Now picture that same pond, except the ripples appear and vanish on their own without anyone throwing a stone. That's the quantum vacuum for you, a cosmic pond where energy and particles flicker in and out of existence without any obvious cause. These fleeting disturbances are called quantum fluctuations, and they turn our classical understanding of physics upside down. According to the laws of quantum mechanics, empty space is never truly empty. Instead, it's a boiling sea of virtual particles, electrons, quarks, even photons that materialize for the tiniest fraction of a second before annihilating each other. These fluctuations aren't just mathematical quirks. We've actually detected their effects in experiments like the Casimir Effect, where invisible forces emerge from nothingness, pushing metal plates together purely because of this ephemeral particle dance. But here's where things get mind-bending. These fluctuations aren't just laboratory curiosities. They might hold the universe together. Without them, atoms could collapse, fundamental forces might unravel, and the very fabric of reality would behave unpredictably. At the same time, they also hint at something stranger, the possibility that the vacuum itself contains energy, an idea that connects to the greatest cosmic mysteries, from dark energy to the birth of universes. So next time you think of empty space, remember, it's anything but quiet. It's a storm of creation and destruction happening all around us every moment we exist. But if the quantum vacuum is never truly empty, then what is it filled with? The answer leads us to one of the most perplexing enigmas in modern physics, something called vacuum energy. Think of it like this: even when you remove all particles, all light, all detectable phenomena from a space, there's still a lingering hum of energy left behind. Not the kind you can harness with wires and circuits, but an intrinsic property of space itself, a kind of baseline buzz woven into the universe's fabric. This idea isn't new. Back in the early days of quantum theory, physicists like Paul Dirac realized that empty space couldn't just be nothing. The same fluctuations that create virtual particles also suggest space has an inherent energy density, a sort of zero-point energy that never disappears even at absolute zero temperature. But here's the catch. When scientists tried to calculate how much energy this vacuum should contain, the numbers spiraled into absurdity. According to theory, the vacuum's energy density should be so immense that it would warp the entire cosmos beyond recognition, yet our universe remains mostly stable. This staggering mismatch between prediction and reality is called the cosmological constant problem and it's been stumping physicists for nearly a century. And then there's dark energy, the mysterious force accelerating the expansion of the universe. When astronomers first discovered this phenomenon in the late 1990s, one startling possibility emerged. Maybe dark energy is vacuum energy. If so, it would mean the same quantum foam we're discussing here isn't just a microscopic curiosity, it's literally shaping the fate of the cosmos on the grandest scales. Yet the numbers still don't add up. The vacuum's predicted energy is outrageously stronger than what we observe dark energy to be. Somewhere in this gap lies a misunderstanding so profound it could rewrite physics. So we're left with a haunting question: is vacuum energy real? If it is, why is its effect so faint? And if it isn't, why does the math insist it must exist? The quantum vacuum refuses to give up its secrets easily, but one thing's certain: solving this riddle could unlock truths about space, time, and existence itself. Picture two thin metal plates placed so close together in a vacuum that there's barely enough room for a single atom to slip between them. According to classical physics, nothing should happen. They're not electrically charged, not magnetized, just inert pieces of metal. Yet, against all intuition, they're pulled together by an invisible force. This isn't magic, it's the Casimir Effect, one of the most jaw-dropping demonstrations that the quantum vacuum is anything but empty. Here's how it works. Between those plates, only certain wavelengths of virtual particles can flicker into existence specifically, ones that fit perfectly in that tiny gap. Outside the plates, though, any wavelength can pop up. This imbalance creates a kind of quantum pressure difference, where the particle swarm outside pushes harder than the restricted fluctuations inside forcing the plates together. It's like being in a crowded subway where the press of bodies on one side shoves you toward the wall, except here, the bodies are ghostly particles that exist for less than an eye blink. The wild part: we've seen this. In 1997, physicists at the University of Washington measured the Casimir effect with astonishing precision, confirming that quantum fluctuations exert real, detectable forces. Since then, labs worldwide have refined these experiments, even demonstrating dynamical Casimir effects, where moving plates fast enough can convert vacuum fluctuations into real photons effectively conjuring light from nothingness. But beyond proving quantum theory's weirdness, this effect has startling practical implications. In nanotechnology, where engineers manipulate structures atom by atom, the Casimir force can sabotage microscopic machines by making components stick together unpredictably. Yet some researchers now explore harnessing it, designing quantum levitation systems or frictionless nanoscale devices that ride vacuum fluctuations like surfers on a wave. Others speculate that mastering this force could lead to breakthroughs in energy extraction, though that remains fiercely debated. So the next time someone says nothing's there in empty space, remember, the Casimir effect proves nothing is never just nothing. The void pushes back. Take a deep breath, because right now, trillions upon trillions of invisible particles are popping into existence all around you, only to vanish before you could even blink. These aren't ordinary matter, they're virtual particles the quantum vacuum's most elusive trick. Unlike the stable protons and electrons that build our world, these ghostly entities live on borrowed time, flickering in and out of reality so fast that they defy direct observation. Yet despite their ephemeral nature, they're the unseen architects of the universe, orchestrating everything from the glow of stars to the fate of black holes. Here's the twist: virtual particles aren't just random noise. They obey strict quantum rules, emerging in particle-antiparticle pairs, like an electron and its mirror opposite, a positron bound by a cosmic IOU. Energy conservation says they can't exist indefinitely, so they annihilate each other almost instantly, returning their borrowed energy to the vacuum. But in that fleeting moment, they become intermediaries for nature's fundamental forces. When two electrons repel each other, for instance, they're not just magically pushing apart, they're exchanging a hailstorm of virtual photons, the force carriers of electromagnetism. It's like two skaters tossing a barrage of invisible balls between them, each catch and throw nudging them further apart. Now amplify this weirdness to cosmic scales and you get Hawking radiation, the slow evaporation of black holes. Near a black hole's event horizon, gravity warps spacetime so drastically that virtual pairs can't always reunite. Sometimes one particle gets swallowed by the hole while the other escapes as real radiation. Over eons, this process siphons mass from the black hole itself, proving even the universe's most voracious monsters aren't immune to the vacuum's quantum whispers. Yet the deeper we look, the stranger it gets. Recent experiments with ultra-strong lasers have hinted that we might one day control virtual particles, coaxing them into observable existence. And if that's possible, could we tap into their energy? The theories are speculative, but the implications are staggering. After all, if even a fraction of this quantum foam could be harnessed, it might rewrite the future of energy, computation, and our understanding of reality itself. For now, though, virtual particles remain both a cornerstone of physics and one of its most tantalizing puzzles, proof that the universe loves to flirt with the impossible. At the very edge of physics lies a concept so counterintuitive, it defies our most basic assumptions about energy and motion: zero-point energy. Even if you could cool a system down to absolute zero, the coldest possible temperature, quantum mechanics insists it would still possess a faint, unshakable hum of energy. This isn't residual heat or some measurement error. It's a fundamental property of reality itself. The universe simply refuses to sit perfectly still. The implications are staggering. If empty space crackles with this baseline energy, could we tap into it? The idea has fueled decades of speculation, from sci-fi dreams of limitless power to serious theoretical proposals. Some suggest that manipulating quantum fields could, in theory, extract usable energy from the vacuum-imagined spacecraft propelled by the fabric of spacetime itself, or cities powered not by burning fuel but by harnessing the faint tremors of existence. Experiments with tiny, vibrating membranes and ultra-cold atoms have even shown hints of zero-point motion at microscopic scales, proving this energy isn't just hypothetical. But here's the catch: extracting it reliably borders on fantasy. Every proposed zero-point energy device collides with the unbreakable laws of thermodynamics. The vacuum's energy is everywhere, but it's also perfectly balanced, like a stretched rubber sheet that can't be cut without snapping back. Attempts to siphon it would require distorting spacetime itself, something far beyond our current technology. Worse, many schemes branded as zero-point energy machines are thinly veiled perpetual motion scams, ignoring the brutal truth. Energy can't be created from nothing, only converted. Yet the mystery persists. If we can't use zero-point energy, why does it exist at all? Some theorists argue it's the scaffolding of reality, a kind of quantum white noise that stabilizes atoms and prevents them from collapsing. Others see it as a clue to deeper physics, hidden in the fine print of the universe's operating manual. One thing's certain: the vacuum's restless energy reminds us that nature abhors true stillness, and that even in the coldest, emptiest corners of existence, there's always a quiet pulse of something more. What if everything you know, every law of physics, every constant holding reality together, could suddenly change not through some cosmic collision or alien superweapon, but because the quantum vacuum itself becomes unstable? This nightmare scenario is called vacuum decay, and it's one of the most unsettling ideas in theoretical physics. Here's how it could work. The universe might not be sitting in the true lowest energy state. Instead, our vacuum could be metastable, a precarious ledge, like a ball balanced on a hill, where one tiny nudge could send it tumbling into an entirely new state of existence. The trigger: a single quantum fluctuation could do it. If a small pocket of space suddenly transitioned to this lower energy, true vacuum, It would create an expanding bubble where the fundamental forces, gravity, electromagnetism, even nuclear interactions operate under new rules. The bubble's boundary would race outward at nearly the speed of light, rewriting physics in its wake. Atoms might unravel, particles could cease to behave as they once did, and the very fabric of space-time could morph into something unrecognizable. By the time we noticed, it would already be too late, but before panic sets in, let's be clear, this isn't a doomsday forecast. The odds of spontaneous vacuum decay are astronomically low. Our universe has lasted 13.8 billion years without collapsing, which suggests either the vacuum is extremely stable, or we're incredibly lucky. Some calculations even hint that the Higgs field, which gives particles mass, might be slightly metastable, but the timescales for decay exceed the age of the universe by trillions of years. Still, the fact that it's theoretically possible forces us to confront a humbling truth. The laws of physics we take for granted might not be eternal. And here's the twist: if vacuum decay did happen, we wouldn't see it coming. No warning, no dramatic explosion, just an invisible wall of new physics approaching at light speed. Some theorists argue that advanced civilizations might one day trigger decay intentionally to reshape reality for their own purposes, though that veers into wild speculation. For now, vacuum decay remains a chilling what-if at the fringes of cosmology, a reminder that even the emptiest corners of existence could hold surprises we can't yet imagine. The universe, it seems, never runs out of ways to keep us guessing. There's an invisible field stretching through every inch of the universe, one you've never seen, never felt, but couldn't exist without. This is the Higgs field, the cosmic molasses that slows down certain particles and gives them the gift of mass. Without it, electrons would zip through space at light speed, atoms would never form, and you, along with everything else, would dissolve into weightless chaos. But here's the twist: the Higgs field isn't some distant abstraction. It's woven into the very fabric of the quantum vacuum, turning empty space into something far more mysterious than we ever imagined. Picture the vacuum as a vast, invisible ocean, and the Higgs field as its current. Particles moving through it interact like swimmers fighting against the tide. Some, like photons, glide through effortlessly. That's why light has no mass, while others, like quarks, drag as if weighed down by invisible anchors. The stronger a particle's interaction with this field, the heavier it becomes. This isn't just poetic metaphor. It's been confirmed by the Large Hadron Collider, where the discovery of the Higgs boson in 2012 proved the field's existence by catching a fleeting ripple in its fabric. Now let's crank up the strangeness. The Higgs field's current strength isn't arbitrary. It's determined by the vacuum's lowest energy state, but disturbingly, calculations suggest this value might not be set in stone. Theoretical models hint that the Higgs could exist in an even lower energy configuration, a possibility that ties directly into the nightmare of vacuum decay. If the field's value somehow shifted, even slightly, the ripple effects would rewrite physics overnight. Atoms could fly apart, stars might collapse under new rules of gravity, and the universe as we know it would cease to function. Yet there's a silver lining. The Higgs field's stability or instability depends on the very quantum fluctuations we've been exploring. Some theories suggest that the vacuum's chaotic dance of virtual particles might act as a kind of cosmic glue, holding the Higgs at its current value against all odds. Others speculate that undiscovered particles or forces could be silently reinforcing the field, like invisible scaffolding propping up reality itself. So while the Higgs field might seem like an abstract concept, it's actually the silent architect of mass, the hidden hand shaping everything from the tiniest atom to the largest galaxy. And its precarious connection to the quantum vacuum reminds us, the universe's most fundamental rules might be more fragile than we ever dared to think. The universe loves symmetry except when it doesn't. Picture a pencil perfectly balanced on its tip. In theory, it's symmetrical, identical in every direction. But the slightest breeze sends it tumbling, breaking that symmetry as it lands lopsided on your desk. Now, imagine that same principle governing the fundamental forces of nature, and you've stumbled upon one of the quantum vacuum's most profound tricks, spontaneous symmetry breaking asterisk. Here's the catch: the laws of physics themselves often treat all directions, all particles, all outcomes as equal, yet the world we see is anything but. The quantum vacuum's lowest energy state, its preferred configuration, doesn't always reflect that perfect symmetry. Instead, like that falling pencil, it settles into an uneven reality. This mismatch between cosmic rules and cosmic reality is the hidden engine behind some of the universe's most critical phenomena, including the very existence of mass. Take the Higgs field. In its symmetrical state, all particles would zip around massless, indistinguishable. But in our universe, the field's lowest energy state is lopsided like a valley with countless hills, where the Higgs rolled downhill to settle into one uneven configuration. That shift broke the symmetry, giving particles their differing masses. Without this cosmic imbalance, atoms couldn't form, chemistry wouldn't exist, and life as we know it would be impossible. But the strangeness doesn't stop there. Spontaneous symmetry breaking might also explain why our universe has more matter than antimatter, an asymmetry that allowed stars, planets, and us to exist. Some theories suggest the quantum vacuum's uneven settling in the earliest moments of the Big Bang tipped the scales, favoring matter just slightly. If true, it means the imperfections of empty space didn't just shape physics. They shaped us. And here's the kicker: this process isn't some ancient relic. Superconductors, materials that let electricity flow without resistance, rely on a similar breaking of symmetry at ultra-cold temperatures. Even a magnet's stubborn north and south poles emerge from this same quantum quirk. The lesson: the universe's love of symmetry isn't about perfection, it's about potential. The quantum vacuum doesn't play by the rules we expect, and that's exactly why reality works the way it does. So the next time you hold a magnet or flip a light switch, remember, the universe's greatest tricks happen when it decides to lean just a little off-center. And in that tilt, everything from atoms to galaxies finds its footing. Beneath the smooth surface of space-time, down at distances so small they make atoms look like giant boulders, reality takes on a bizarre new texture. This is the realm of quantum foam, a turbulent, seething mess where space and time themselves lose all semblance of order. Here, the fabric of the universe isn't just warped or bent, it's shredded into a constantly churning froth of microscopic black holes, wormholes, and fluctuating geometry. The concept traces back to physicist John Wheeler, who realized that at unimaginably tiny scales, around 1/10 trillionth the width of a proton, quantum uncertainty makes spacetime anything but stable. Gravity, normally so smooth and predictable, erupts into violent fluctuations. Tiny regions of space might briefly collapse into microscopic black holes, only to vanish moments later. Wormholes could form and dissolve like bubbles in a boiling pot, connecting distant points in space before snapping shut. It's as if the universe's foundation is built on quicksand, constantly churning beneath our feet. Why does this matter? Quantum foam might be the missing link between Einstein's theory of gravity and quantum mechanics, two pillars of physics that stubbornly refuse to cooperate. In this chaotic dance at the Planck scale, the smooth curves of relativity collide with the jittery unpredictability of quantum theory. Some researchers believe that unlocking the secrets of quantum foam could finally reveal our theory of everything a single framework explaining all forces in nature. The catch: we can't observe it directly, yet the scales involved are so infinitesimal that even our most powerful particle colliders glimpse only indirect hints. But ingenious experiments are probing the edges of this frontier. Certain models predict that ultra-high-energy cosmic rays traveling across billions of light-years might carry subtle scars from spacetime's frothy nature. Others suggest that precise quantum sensors could someday detect the faint noise of spacetime itself fluctuating. One thing's certain: if quantum foam is real, it rewrites our most basic assumptions about reality. Space isn't an empty stage, it's an ever-changing, turbulent ocean. And if we ever learn to navigate its currents, we might just find the universe's deepest truth swirling in the chaos. Astronomers made a discovery in the late 1990s that sent shockwaves through cosmology. The universe isn't just expanding, it's doing so at an ever-increasing pace. This mysterious force, dubbed dark energy, behaves like an anti-gravity pushing galaxies apart. But here's where things get surreal. The leading explanation points straight back to the quantum vacuum. The math suggests vacuum energy should act just like dark energy, a constant pressure embedded in space itself. There's just one colossal problem. The numbers disagree by a factor of 10 followed by *120 zeros *. It's the widest mismatch between theory and observation in all of physics. Some researchers call it the worst theoretical prediction in history. If vacuum energy were truly as powerful as calculations suggest, galaxies would have torn apart before stars could even form. Yet our cosmos exists calmly, steadily accelerating at a rate that defies expectations. This glaring discrepancy has sparked fierce debate. Could our understanding of quantum fields be fundamentally flawed? Maybe vacuum energy isn't uniform but varies across space in ways we can't yet detect. Or perhaps dark energy isn't vacuum energy at all, but something entirely different, a new field or modified gravity. Alternatives like quintessence propose a dynamic energy that changes over time, unlike the rigid constancy of vacuum predictions. Meanwhile, cutting-edge telescopes like the Dark Energy Survey and Euclid are mapping the universe's expansion with unprecedented precision, hunting for clues in the subtle warping of starlight or the distribution of galaxies. Each new dataset either tightens the knot or offers a thread we might pull to unravel the mystery. One thing's clear: the quantum vacuum and dark energy are entwined in ways we're only beginning to grasp. And solving this riddle won't just explain the fate of the cosmos, it might reveal entirely new physics hiding in plain sight. Crossing the event horizon of a black hole would mean certain doom. But what if just moving fast enough could conjure particles from nothingness? Welcome to the Unruh Effect, where acceleration rewrites the rules of reality itself. Picture two astronauts, one floating peacefully in empty space, the other strapped to a rocket hurtling at breakneck speeds. To the first, the vacuum is silent and still, exactly what you'd expect from nothing. But for the astronaut under acceleration, the same void crackles with heat. A faint glow of particles appears where none existed before, simply because their motion distorts the quantum soup beneath spacetime. This isn't hypothetical wordplay. The Unruh effect emerges directly from the marriage of Einstein's relativity and quantum field theory. Acceleration, it turns out, doesn't just change your speed, it alters your very perception of reality. Like a surfer carving through waves, an accelerating observer slices through the quantum vacuum in a way that reveals particles invisible to someone coasting along. The faster the acceleration, the hotter this phantom glow becomes. Approach a trillion g-forces, and the vacuum would shimmer with heat akin to the surface of the sun, all from sheer motion alone. But here's the twist: these particles aren't just illusions. They carry real energy, real consequences. Some theorists suggest that wildly accelerating observers might even see different physics like altered decay rates for particles or shifted quantum probabilities. This raises a provocative question: is there an objective, empty space, or does it depend entirely on how you're moving? the Unruh effect blurs the line between observer and environment in a way even Einstein might find startling. Detecting this phenomenon directly remains a towering challenge. Human-scale accelerations produce temperatures colder than the deepest void. Yet ingenious lab setups like ultra-sensitive detectors in particle colliders or future experiments with laser-trapped atoms might one day catch whispers of this acceleration-induced mirage. And if they do, it could force us to confront an unsettling truth. The universe has no fixed stage. Reality, it seems, is a dance between what's there and how you choose to look. Mystery 12. Vacuum polarization. Even light doesn't escape the quantum vacuum's influence. When a beam travels through empty space, it isn't just passing through nothing. It's navigating a seething sea of virtual particles that subtly reshape its path. This bizarre phenomenon, called vacuum polarization bends the rules of electromagnetism in ways that defy classical intuition. Here's what's happening. When an electric charge, say an electron, sits in the vacuum, it doesn't just interact with the world around it. The surrounding quantum foam responds by sprouting temporary pairs of virtual particles, particularly electrons and their antimatter twins, positrons. These pairs act like microscopic magnets, aligning themselves in a way that screens the original charge. It's as if the electron is wearing a cloak of flickering particle-antiparticle duos, slightly blurring its electromagnetic influence. The closer you get, the more this screening effect weakens, revealing the charge's true strength. This isn't just theoretical sleight of hand, it leaves fingerprints in real-world physics. In the late 1940s, physicists Willis Lamb and Robert Rutherford spotted a tiny anomaly in hydrogen atoms. When electrons jumped between specific energy levels, their measured frequencies didn't match predictions. The discrepancy, now called the Lamb shift was a direct consequence of vacuum polarization. Those fleeting virtual particles slightly warped the electron's environment, tweaking its energy in ways only quantum theory could explain. But the implications stretch far beyond atomic labs. Vacuum polarization affects how particles scatter in high-energy collisions, subtly altering outcomes in particle accelerators like the Large Hadron Collider. Even the cosmic microwave background, the afterglow of the Big Bang, carries faint imprints of this quantum dressing. Some theories suggest that in extreme environments like near-neutron stars, vacuum polarization could magnify electromagnetic fields to staggering intensities. So next time you flip on a light, remember, the photons racing toward your eyes aren't just surfing empty space. They're threading through an invisible quantum tapestry, where even the void has a say in how the universe behaves. Picture two coins flipped simultaneously on opposite sides of the universe, yet somehow, every time one lands heads, the other instantly lands tails, no matter how far apart they are. This isn't magic, it's the essence of the EPR paradox a thought experiment so unsettling that even Einstein called it spooky action at a distance. But here's where the quantum vacuum turns this puzzle into something even stranger. What if this eerie connection isn't just about particles, but the very fabric of empty space itself? In 1935, Einstein and his colleagues Podolsky and Rosen proposed a scenario to expose what they saw as quantum mechanics absurdity. Imagine two particles born from the same quantum event, then flung light years apart. Measure one spin, and its twin spin instantly snaps into the opposite state, defying the speed of light limit Einstein himself established. The trio argued this proved quantum theory was incomplete, that hidden variables must secretly govern these particles. But decades later, experiments confirmed the spookiness was real. Particles influence each other across vast distances through a phenomenon called quantum entanglement Now, layer in the quantum vacuum's role. Empty space isn't just a passive backdrop for these entangled pairs, it's an active participant. Virtual particles constantly popping in and out of existence can become entangled too, linking regions of the vacuum in ways that challenge our notions of locality, the idea that objects are only influenced by their immediate surroundings. Some theories even suggest that entanglement might originate from the vacuum structure, with spacetime itself acting as a silent conductor for these ghostly correlations. This raises a profound question. Is reality fundamentally interconnected at levels we're only beginning to glimpse? The vacuum's entanglement hints that separateness might be an illusion, that the universe operates more like a cosmic web than a collection of isolated points. Experiments with superconducting circuits and photon pairs are now probing this frontier, testing whether vacuum fluctuations play referee in these non-local connections. Yet for all the progress, the EPR paradox lingers like a thorn in physics' side. If entanglement threads through the vacuum, does that mean space itself holds a kind of memory? Or are we missing a deeper layer of reality altogether? The answers could reshape everything from quantum computing to our understanding of causality. One thing's certain, Einstein's spookiness is far from dead. It's woven into the void, waiting to be unraveled. Mystery 14. Schwinger Effect ***. Even the vacuum has its limits, and when pushed hard enough, it breaks in spectacular fashion. Picture an electric field so powerful it tears space itself apart, literally ripping matter from nothingness. This isn't hyperbole. It's the Schwinger Effect ***, a quantum phenomenon where empty space, under extreme duress, coughs up real particles as if surrendering to physics' most relentless interrogation. The principle traces back to Nobel laureate Julian Schwinger, who predicted in the 1950s that an electric field beyond a critical threshold, around 1 quadrillion volts per meter, could wrench virtual particle pairs from the vacuum before they have a chance to annihilate. Normally, these fleeting duos borrow energy from the vacuum and vanish in an instant, debt unpaid. But under a sufficiently strong field, the particles get yanked in opposite directions with such force that they can't recombine. The energy loan becomes a permanent withdrawal, leaving behind real, detectable particles. It's like stretching a rubber band until it snaps, except here the rubber band is space-time, and the snap births matter from pure energy. For decades, this effect existed only in theory. The electric fields required were beyond anything we could generate, but modern lasers are changing the game. Facilities like the European Extreme Light Infrastructure now fire pulses so intense, even their fleeting focus creates electric fields approaching Schwinger's threshold. In 2020, an experiment at CERN High-Rad-Mat facility used high-energy proton beams to mimic the effect, observing telltale signs of particle production in eerily empty spaces. Yet the full effect remains tantalizingly out of reach. To truly break the vacuum, we'd need fields so strong they briefly rival the forces inside a neutron star. Some researchers propose colliding ultra-intense laser beams or harnessing plasma wake fields to cross that final frontier. If successful, it wouldn't just confirm Schwinger's math, it would prove that the vacuum isn't just a stage for particles, but a participant in their creation. And the implications staggering. Mastering this effect could unlock new ways to study particle physics without massive colliders, probe the origins of cosmic rays, or even, in distant futures, engineer energy extraction from spacetime itself. Of course, those possibilities teeter on the edge of speculation. But one thing's certain, the Schwinger effect reveals the vacuum as something far richer than emptiness. It's a reservoir of potential matter waiting for the right spark to bring it to life. Mystery 15. Bekenstein-Hawking entropy ** black holes are often called the universe's ultimate garbage disposals, swallowing everything that crosses their path, never to return. But what if these cosmic voids aren't just chaotic pits of destruction? What if they hide a hidden order, a kind of cosmic ledger keeping track of every bit of information they consume? That's the startling revelation behind Bekenstein-Hawking entropy asterisk, a discovery that ties black holes to the quantum vacuum in ways no one saw coming. Here's the puzzle. In everyday life, entropy measures disorder. Think of a melted ice cube or a shuffled deck of cards. But black holes, according to classical physics, were supposed to be perfectly featureless. No hair, no complexity, just mass, charge, and spin. Then in the 1970s, physicist Jacob Bekenstein made a radical proposal. Black holes must have entropy, a way to account for all the chaos they devoured. Stephen Hawking later proved it mathematically, showing that a black hole's entropy isn't just real, it's proportional to the area of its event horizon. But where does this entropy come from? That's where the quantum vacuum barges in. At the very edge of a black hole's event horizon, virtual particles flicker in and out of existence like always. But in this extreme gravitational grip, things get messy. Some particles fall in, while others escape as Hawking radiation. This slow leak causes the black hole to shrink over time, meaning its entropy, its hidden information, must somehow be encoded in those outgoing particles. The real shocker, the math suggests that every bit of information swallowed by a black hole gets painted onto its surface, etched into the event horizon in Planck-sized pixels. It's as if the vacuum fluctuations at the boundary act like a cosmic hard drive, storing data we once thought was lost forever. This bizarre link between thermodynamics and quantum gravity could finally crack open one of physics' toughest problems. How do we reconcile the smooth, continuous spacetime of general relativity with the jittery, pixelated world of quantum mechanics? Some theories now suggest that all spacetime might secretly operate like this, that the universe itself could be a hologram, with information encoded on its boundaries rather than within its volume. If true, black holes aren't just cosmic anomalies, they're Rosetta Stones, revealing a hidden layer of reality where gravity and quantum mechanics shake hands. For now, the details remain hazy, but one thing's certain: the quantum vacuum isn't just a passive player here. It's the silent scribe, keeping track of the universe's deepest secrets, one black hole at a time. Mystery 16. The Vacuum Catastrophe ***. There's a number so colossal, so mind-bendingly wrong, it's been called the worst prediction in the history of physics. Imagine calculating the weight of a feather and getting an answer heavier than the entire observable universe. That's essentially what happens when theorists try to pin down the energy density of the quantum vacuum. The math says it should be unimaginably powerful, yet our telescopes see only the faintest whisper of its effect. This colossal mismatch, spanning 120 orders of magnitude is the Vacuum Catastrophe and it's one of science's most glaring unsolved puzzles. Let's break down the absurdity. Quantum field theory predicts that the vacuum isn't empty, it's a churning sea of fleeting particles and fields, each contributing a tiny bit of energy. Add it all up, and the total vacuum energy density should be enormous enough to warp spacetime so violently that stars and galaxies could never form. Yet when astronomers measure the actual energy driving the universe's expansion, our dark energy, it's laughably weaker, like comparing a supernova to a candle flicker. The gap between prediction and reality isn't just a rounding error. It's a screaming red flag that something fundamental is missing from our understanding. Theorists have thrown everything at this problem. Maybe our calculations are double-counting quantum effects, or perhaps unknown symmetries cancel out the vacuum's energy in ways we haven't discovered. Some suggest dark energy isn't vacuum energy at all, but an entirely new force that mimics its behavior. Others propose radical fixes, like extra dimensions soaking up the excess energy, or an undiscovered screening mechanism that hides the vacuum's true strength. Meanwhile, experiments are closing in. ultra-precise measurements of distant supernova, galaxy clusters, and the cosmic microwave background keep refining dark energy's value, hoping to spot a deviation that hints at deeper physics. Quantum labs are probing vacuum fluctuations with ever more sensitive tools, hunting for anomalies that might reconcile theory and observation. The stakes couldn't be higher. Crack this puzzle, and we might finally understand why the vacuum is so eerily quiet, and whether its silence is a fluke or a clue to a grander cosmic design. Until then, the Vacuum Catastrophe stands as a humbling reminder. Sometimes the universe's loudest mysteries come from the emptiest places. Mystery 17. Phantom energy right now. The universe is stretching apart, galaxies drifting away, space itself expanding. But what if that expansion didn't just continue? What if it exploded? Not in fire and light, but in an unstoppable, silent unraveling of reality itself. This is the nightmare scenario known as phantom energy a hypothetical twist on vacuum energy so bizarre. It predicts the cosmos will one day rip itself to shreds in a cataclysm called the Big Rip Most models of dark energy assume its strength stays constant over time, like a gentle push on the cosmic gas pedal. Phantom energy, though, is different. It's a rogue form of vacuum energy that doesn't just persist it grows . Imagine blowing up a balloon where every breath you add makes the rubber thinner and easier to stretch. Now replace the balloon with space-time, and you've got the essence of phantom energy. Over billions of years, its pressure would intensify, accelerating the universe's expansion so violently that even atoms couldn't hold together. Here's how the end would unfold. First, distant galaxies vanish as space between us and them stretches faster than light can cross it. Next, galaxy clusters, then individual galaxies are torn apart. Stars flee their own solar systems, planets disintegrate. In the final moments, even atomic nuclei, the last bonds holding matter together, would be wrenched apart. The universe wouldn't just fade into cold darkness, it would dissolve into a sea of lonely, irretrievable particles, each lost in an infinite, ever-widening void. But before you brace for doomsday, there's a catch. Phantom energy is purely theoretical, no direct evidence yet supports its existence. Some physicists argue it's mathematically plausible within certain string theory or quantum gravity models, while others dismiss it as a troubling quirk of equations. The real intrigue, even if phantom energy is real, its timeline is mercifully long. Current estimates suggest the Big Rip, if it happens at all, wouldn't occur for another 100 billion years long after our sun has burned out. Yet the idea haunts cosmology for a reason. If phantom energy does lurk in the vacuum, it means the universe's expansion isn't just a fact, it's a ticking clock. And that forces us to confront a haunting question. Is the vacuum truly stable, or is it hiding a self-destruct mechanism buried in its deepest equations? For now, the answer hovers just beyond our grasp, somewhere in the quantum static between what we know and what we fear. Might be possible. Mystery 18. The vacuum in the early universe for the tiniest fraction of a second after the Big Bang, something extraordinary happened. The universe didn't just expand, it exploded outward faster than the speed of light. This mind-bending moment, called cosmic inflation stretched space so violently that quantum fluctuations, those tiny ripples in the vacuum, were blown up to cosmic proportions. And those microscopic tremors, they became the blueprint for everything we see today: galaxies, stars, even the vast web of dark matter connecting the cosmos. Think of it like blowing up a balloon with tiny wrinkles on its surface. Inflate it enough, and those once minuscule creases stretch into massive ridges. In the same way, the quantum vacuum's fluctuations during inflation didn't vanish, they got frozen into the fabric of spacetime itself. Denser regions became gravitational wells, pulling in matter to form galaxies, while lighter areas expanded into the cosmic voids we see between them. The universe's entire structure, from the smallest galaxy cluster to the grandest supervoid, owes its existence to these quantum whispers magnified beyond imagination. But here's the twist. Inflation didn't just amplify these fluctuations, it *stamped them with a telltale signature. The pattern left behind matches exactly what we see in today's cosmic microwave background, the afterglow of the Big Bang. Satellite missions like Planck have mapped these faint temperature variations with astonishing precision, revealing a near-perfect echo of the vacuum's quantum behavior from 13.8 billion years ago. It's as if the universe took a snapshot of its own infancy and the quantum vacuum was the artist, yet mysteries remain. Why did inflation start or stop? What triggered the vacuum to release its energy, ending the exponential expansion and reheating the universe into the fiery plasma we recognize as the Big Bang? Some theories suggest a phase transition in the vacuum itself, like water freezing into ice, could have flipped the switch. Others propose that inflation wasn't a one-time event, but part of an endless cycle where new universes bud off from the quantum foam like bubbles in a vast cosmic sea. One thing's certain, the vacuum in those first moments wasn't passive. It was the engine behind the universe's growth, the hidden sculptor of everything from galaxy clusters to the atoms in your body. And buried in the faint wrinkles of spacetime, its fingerprints are still waiting to be read. Mystery 19. The holographic principle ***. What if everything you see, the stars, the planets, even your own hands, is nothing more than an illusion? Not in a philosophical sense, but as a fundamental property of reality itself. This is the heart of the **** holographic principle ***, a radical theory suggesting that our three-dimensional universe might actually be a projection of information stored on a two-dimensional surface at its boundary. And where does this mind-bending idea connect? Right back to the quantum vacuum. The principle first arose from an unexpected discovery about black holes. As we saw earlier, the entropy of a black hole, its hidden information is proportional to the **area* of its event horizon, not the volume inside. This hinted at something astonishing. All the complexity, all the data making up everything swallowed by the black hole, could be encoded on its surface like a cosmic hard drive. Extend this idea to the entire universe, and you get the holographic principle, a suggestion that reality might work like a movie screen, with the vacuum's fluctuations painting the illusion of depth where there's only flat data. Here's where it gets even stranger. In this framework, the quantum vacuum isn't just empty space, it's more like the pixels of a vast cosmic display. Every particle, every force we experience in 3D could be the result of information processing happening on a distant, unseen surface. It's as if the universe is running on a kind of quantum code, with the vacuum acting as the interface between the real data and the world we perceive. But does this hold up beyond theory? Surprisingly, yes. Certain models of quantum gravity, like string theory, naturally incorporate holographic duality, showing that a higher dimensional universe can mathematically translate to a lower dimensional one without losing information. Experiments with superconductors and entangled particles have even uncovered behaviors that mirror holographic predictions, though we're still far from definitive proof. The implications would rewrite physics as we know it. If the holographic principle is true, then entanglement, dark energy, even spacetime itself might just be emergent phenomena, side effects of a deeper, more fundamental layer of reality we can't yet see. It's a humbling thought. The vast cosmos, with all its galaxies and wonders, might be nothing more than a shimmering mirage on the surface of the void. So the next time you gaze at the night sky, remember, What you're seeing might not just be asterisk out there asterisk. It could be written on the universe's edges, a cosmic illusion crafted by the quantum vacuum's invisible hand. Asterisk asterisk mystery 20. Time crystals asterisk asterisk. Imagine a clock that ticks forever without winding, without batteries, without any energy at all. It sounds impossible, yet in the bizarre world of quantum physics, such a thing exists. Meet asterisk time crystals asterisk, structures that don't just sit idle in their lowest energy state. They pulse, rotate, or oscillate endlessly, as if the universe handed them a perpetual motion cheat code. And the secret behind their defiance of conventional physics, the quantum vacuum itself. Unlike ordinary crystals like diamonds or snowflakes where atoms arrange themselves in repeating patterns asterisk in space asterisk, time crystals repeat asterisk in time asterisk. Their components move in a cycle, returning to their starting positions at regular intervals, even in their ground state. Normally, anything in its lowest energy state should be still, like a ball resting at the bottom of a valley. But time crystals are more like a ball that rolls back and forth forever between two identical valleys without losing energy, a phenomenon made possible by subtle quantum nudges from the vacuum's fluctuations. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, initially met with skepticism. How could something move perpetually without breaking the laws of thermodynamics? The answer lies in asterisk symmetry breaking asterisk, just as spatial crystals break the symmetry of space by choosing a specific arrangement of atoms. Time crystals break the symmetry of asterisk time asterisk by preferring certain moments over others, all while staying in equilibrium. In 2017, two separate teams of researchers brought time crystals to life in the lab. One used a chain of ytterbium atoms, the other a diamond riddled with nitrogen defects. Both systems, when gently tickled with lasers or microwaves, fell into a rhythmic dance that persisted long after the initial push, a proof that time crystals weren't just mathematical quirks but real, observable phenomena. What makes this even stranger is the role of the quantum vacuum. The same virtual particles and fluctuations that shape black holes and particles also seem to feed time crystals, allowing them to sustain their oscillations without energy input. Some theories suggest time crystals could even emerge spontaneously in certain vacuum conditions, hinting that the universe might naturally harbor these strange structures in extreme environments. Practical applications, still speculative but thrilling. Time crystals could revolutionize quantum computing by stabilizing qubits against decoherence or act as ultra-precise quantum sensors. But their real magic lies in what they teach us, that even in its lowest energy state, the universe refuses to sit still. The quantum vacuum isn't just a backdrop, it's a director choreographing reality's most impossible performances. And time crystals, they're the first dancers we've managed to glimpse on this hidden stage. Asterisk asterisk mystery 21. Quantum tunneling from the vacuum asterisk asterisk. Picture a ball rolling toward a hill. In the everyday world, if it doesn't have enough energy to reach the top, it rolls back down, simple as that. But in the quantum realm, that same ball occasionally asterisk phases straight through the hill asterisk, as if the barrier weren't even there. This isn't magic, it's asterisk asterisk quantum tunneling asterisk asterisk, a phenomenon where particles cheat their way through impossible barriers, all thanks to the restless churn of the quantum vacuum. At the heart of this lies uncertainty. In a universe governed by quantum mechanics, particles aren't just tiny marbles with fixed positions. They're more like clouds of probability, flickering in and out of potential states. Thanks to vacuum fluctuations, there's always a tiny chance, however improbable, that a particle will suddenly find itself asterisk on the other side asterisk of an energy barrier it couldn't classically overcome. It's as if the vacuum's chaos hands particles a momentary free pass, letting them bypass physics' usual rules. This isn't just a lab curiosity, it's the hidden force behind some of nature's most essential processes. Take the Sun, for instance. At its core, protons repel each other fiercely due to their positive charges. Yet, against all classical expectations, they fuse together, unleashing the energy that lights our world. How quantum tunneling? Those protons don't smash through their mutual electric barrier, they tunnel through it, nudged along by the vacuum's probabilistic whims. Without this effect, stars wouldn't shine, and the universe would be cold and dark. Closer to home, tunneling powers modern technology. Your smartphone's flash memory relies on electrons tunneling through insulating layers to store data. Scanning tunneling microscopes let scientists image individual atoms by precisely controlling electron jumps across gaps. Even the transistors in cutting-edge quantum computers exploit tunneling to shuttle information at lightning speeds. But the real mystery is why the vacuum permits this loophole. Some theories suggest tunneling reveals spacetime's inherently fuzzy nature, that on the smallest scales, barriers aren't as solid as they seem. Others propose it's evidence of parallel universes momentarily intersecting, though that remains speculative. What's certain, the quantum vacuum doesn't just host particles, it bends the rules for them, proving once again that impossible is just a word, not a law. So next time you charge your phone or bask in sunlight, remember, invisible quantum shortcuts are at work, all because empty space refuses to play by the rules we expect. Mystery 22. Vacuum and wormholes. Science fiction loves wormholes, cosmic shortcuts bending space to connect distant points in an instant. But what if these tunnels through spacetime aren't just Hollywood fantasy? Buried in the math of general relativity, wormholes appear as valid solutions, yet they all share one fatal flaw. They collapse faster than they form, crushed by their own instability. Unless that is the quantum vacuum steps in. Here's the puzzle: to hold a wormhole open long enough for anything or anyone to traverse it, you'd need something to prop it against gravity's relentless squeeze. Normal matter won't cut it, even the densest star stuff is too weak. But vacuum energy, that's where things get intriguing. Theoretically, certain configurations of negative energy, like the kind produced by quantum fluctuations, could act as cosmic scaffolding, reinforcing the wormhole's throat long enough to make it usable. Imagine threading a wormhole's walls with a kind of quantum anti-gravity, where the vacuum's restless energy pushes outward just enough to counterbalance collapse. The idea isn't pure speculation. Physicists like Kip Thorne and Miguel Alcubierre have shown that if you could harness exotic matter or energy with negative pressure, traversable wormholes become mathematically plausible. And while we've never observed such matter naturally, the quantum vacuum routinely spawns particles with negative energy densities, like those fleeting virtual pairs in the Casimir Effect. Scale that up, and you've got a potential ingredient for wormhole engineering. Of course, the hurdles are cosmic. Generating enough negative energy to stabilize even a microscopic wormhole would require feats far beyond current tech. Some estimates suggest you'd need to manipulate energy densities comparable to a neutron star's core just to open a hole the size of an atom. And then there's causality. Wormholes could create time loops, violating the laws of cause and effect. Nature hates paradoxes, so unless there's an undiscovered law preventing them, the universe might simply forbid stable wormholes outright. Yet the possibility lingers like a siren call. If vacuum energy can stabilize these spacetime tunnels, could advanced civilizations already be using them? Might we one day crack the code, turning sci-fi dreams into physics labs? For now, wormholes remain tantalizingly out of reach, but in a universe where emptiness seethes with invisible energy, impossible is a challenge waiting to be overturned. Mystery 23. The Dirac sea ***, long before quantum field theory reshaped our understanding of the vacuum, physicist Paul Dirac stumbled onto something astonishing. an ocean of negative energy lurking beneath the surface. Reality, his equations insisted that the universe wasn't just sprinkled with electrons, it was drowning in them, packed so tightly they formed an invisible, infinite sea. At first, this seemed like mathematical madness, but buried in that madness was a prediction so revolutionary, it changed physics forever: the existence of antimatter. Here's the puzzle Dirac faced. His own equations described electrons with eerie precision except for one glaring flaw. They kept spitting out solutions where electrons could have negative kinetic energy, something that defied all physical intuition. Rather than ignore these rogue answers, Dirac proposed something radical. What if every possible negative energy state was already occupied by an unseen electron? In this model, the vacuum wasn't empty, it was a churning, Dirac sea, packed wall to wall with invisible negative energy particles. Only the rare gaps in this sea, like bubbles rising in water, would manifest as the familiar electrons we observe. But the real shock came when he asked, what happens if you knock an electron out of this sea? The hole it leaves behind wouldn't just be an absence, it would behave like a particle with positive charge. In 1931, Dirac boldly declared this hole was a new kind of matter, the positron, the electron's antimatter twin. Just a year later, cosmic ray experiments confirmed it. Positrons were real, making Dirac's once dismissed see the first hint that nature plays a perfect game of symmetry between matter and antimatter. Today, we know the Dirac sea isn't the full story. Quantum field theory replaced this infinite ocean with the dynamic vacuum we now recognize, where particle-antiparticle pairs flicker in and out of existence. Yet Dirac's intuition was eerily prescient. His sea foreshadowed concepts like vacuum polarization and even the idea that empty space crackles with hidden activity. It also left us with a haunting question. If antimatter is just matter's mirror image, why does our universe overwhelmingly favor one over the other? The answer might still be hiding in the quantum depths, waiting to surface. So next time you hear about antimatter in sci-fi or medical PT scans, remember it all traces back to one physicist's wild gamble on an invisible sea. Sometimes the strangest ideas aren't just stepping stones, they're portals to entirely new worlds. Mystery 24. Vacuum in quantum computing inside the coldest, most carefully controlled labs on Earth, scientists are building machines that defy classical logic quantum computers. These aren't just faster versions of your laptop, they're devices that tap into the quantum vacuum itself to perform calculations that would take conventional computers millennia to crack. The secret: encoding information not in ordinary bits, but in qubits particles that exploit the vacuum's bizarre properties to exist in multiple states at once. Here's how it works. While a traditional bit is either a 0 or a 1, a qubit can be both simultaneously. Thanks to superposition a quantum phenomenon where particles hover in all possible configurations until measured. But maintaining this fragile state is like balancing a pencil on its tip in a hurricane. The slightest disturbance from heat, vibration, or even stray electromagnetic waves can collapse the qubit's delicate dance. That's where the quantum vacuum comes in. By cooling systems to near absolute zero and isolating qubits in ultra-stable environments, engineers effectively freeze the vacuum's fluctuations, creating pockets of calm where superposition can thrive. But the real magic happens with entanglement another vacuum-driven trick. Link two qubits together and their fates become intertwined, no matter the distance between them. Change one and the other instantly responds, an eerie synchronization Einstein famously dismissed as spooky. Yet in quantum computing, this isn't a bug, it's the backbone of exponential speedups. Algorithms harnessing entangled qubits could revolutionize drug discovery, crack unbreakable encryption, or simulate complex molecules with precision impossible for classical machines. The challenge: the same vacuum fluctuations that enable these feats also threaten to disrupt them. Tiny quantum static can introduce errors, forcing engineers to devise clever error correction techniques, some borrowing ideas from black hole physics or even cosmic inflation. Companies like Google and IBM are already testing qubits housed in superconducting loops or trapped ions, each approach battling to tame the vacuum's chaos long enough to unlock its potential. So while quantum computers aren't quite ready to replace your smartphone, their progress hinges on a profound irony. To harness the future of computing, we must first master the oldest empty space in the universe. And if we succeed, the quantum vacuum won't just be a curiosity, it'll be the engine behind the next technological revolution. Mystery 25. Sonoluminescence ***. A tiny bubble, barely visible to the naked eye, collapses in a flask of water, and for a fraction of a second, it erupts with a flash of light so intense it rivals the surface of the sun. This isn't a chemical reaction or an electrical spark. It's sonoluminescence ***, one of the most baffling displays of energy transformation in physics. And at its heart lies a tantalizing question: could the quantum vacuum itself be playing a role in turning sound into light? The phenomenon works like this. When high-frequency sound waves pass through a liquid, they create areas of extreme low pressure, forming microscopic bubbles. As these bubbles collapse under the surrounding liquid's force, something extraordinary happens. The energy focused into that vanishingly small space triggers a burst of ultraviolet or even X-ray light, lasting just picoseconds, trillionths of a second. The temperatures inside these fleeting orbs may soar to tens of thousands of degrees, hotter than the sun's corona. But here's where things get controversial. Traditional explanations point to shock waves and plasma formation. Basically, the bubbles collapse, heating gas inside to incandescence. Yet some researchers argue that these models can't fully account for the light's intensity or spectrum. That's led to a radical alternative. What if the implosion squeezes the quantum vacuum itself, amplifying its fluctuations until they release energy as light? It's a bit like wringing out a soaked towel, except the water you're squeezing is the vacuum's latent energy. Experiments haven't settled the debate. Studies in ultra-pure water or noble gases show sonoluminescence's light varies in ways that don't always align with classical heating alone. Meanwhile, theorists crunch the numbers on whether vacuum effects could significantly contribute, with some suggesting the bubble's collapse might briefly warp spacetime enough to kick virtual particles into observable photons. Practical applications loom on the horizon. If we could harness this effect efficiently, it might offer new ways to induce nuclear fusion at small scales or create ultra-precise medical imaging tools. For now, though, sonoluminescence remains a dazzling enigma, a fleeting union of sound, light, and perhaps the quantum void itself, reminding us that even the simplest systems can hide universe-shaking secrets. And every flicker in that dark flask is a whisper from the vacuum, challenging us to listen closer. Mystery 26. Vacuum metamaterials ***. What if you could bend light in ways that defy the laws of physics, shattering the limits of resolution, crafting lenses sharper than anything nature allows, even cloaking objects from view? This isn't science fiction, it's the cutting-edge world of vacuum metamaterials ***, where scientists engineer structures so finely tuned they don't just interact with light. They twist the very quantum vacuum itself to their will. The secret lies in materials built with nanostructures smaller than the wavelengths of light they're designed to control. Picture a microscopic coral reef, its branches and gaps precisely arranged to redirect electromagnetic waves in impossible ways. But here's where the quantum vacuum steps in. These metamaterials don't just guide light, they reshape the vacuum's fluctuations around them, amplifying or suppressing virtual particle interactions to achieve effects once deemed unattainable. Take the **perfect lens***, a theoretical device first proposed by physicist John Pendry. Traditional lenses can't focus light beyond a certain resolution, a barrier called the diffraction limit hardwired into classical optics. But metamaterials infused with negative refraction properties sidestep this entirely. By bending light backward, they capture elusive, evanescent waves that normally fade instantly, stitching them back into the image to reveal details smaller than the light's own wavelength. It's like reading the fine print on a sign from miles away, a feat made possible by the vacuum's manipulated behavior at the nanoscale. Beyond lenses, these materials flirt with invisibility. Cloaking devices, long a staple of fantasy, now exist in labs, albeit in limited forms. Metamaterial coatings can reroute light around objects like water flowing around a rock, rendering them partially invisible to specific wavelengths. The quantum vacuum plays a silent role here too. Its fluctuations must be carefully tuned to avoid scattering that would betray the illusion. Yet the grandest promise lies in quantum technologies. Some researchers theorize that vacuum-engineered metamaterials could one day control spontaneous emission **, the random release of light by excited atoms. By sculpting the vacuum's energy landscape, we might dictate when and how particles emit photons, revolutionizing lasers, solar cells, and even quantum communication. Of course, challenges loom. Fabricating these structures demands atomic-level precision, and their effects often work only for narrow bands of light. But with each breakthrough, like graphene-based metamaterials or tunable designs that adapt in real time, the line between impossible and breakthrough blurs further. So while we're not yet handing out perfect glasses or cloaking shields, the message is clear. The quantum vacuum isn't just a backdrop for reality, it's a canvas. And with the right tools, we might just paint a new world atop it. Mystery 27. The vacuum and consciousness **. Some of the most audacious theories in science don't just blur the line between physics and philosophy, they erase it entirely. Enter a provocative idea. What if the quantum vacuum, with its chaotic dance of particles and fields, isn't just shaping the cosmos but consciousness itself? It's a notion that straddles the boundary between groundbreaking and controversial, with researchers fiercely divided over whether it's profound insight or pure speculation. At the heart of these theories lies a striking observation. The brain's neural networks and the quantum vacuum share something unexpected noise. Neurons fire unpredictably, even in the absence of stimuli, much like the random flicker of virtual particles in empty space. Some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose that this isn't coincidence. Their **orch theory suggests that consciousness arises from quantum vibrations in microtubules, tiny structures inside neurons potentially influenced by the vacuum's fluctuations. In this view, the mind isn't just a byproduct of classical physics, it's a quantum symphony tuned by the void. Yet skepticism runs deep. Critics point out that the brain is warm, wet, and chaotic, an environment where delicate quantum states should collapse instantly. Most neuroscientists argue consciousness likely emerges from complex, but purely classical, neural computations. Even proponents admit the evidence is thin. No experiment has definitively linked vacuum fluctuations to cognition. Still, the intrigue persists, fueled by odd parallels. Near-death experiences, for instance, sometimes report vivid awareness during clinical brain shutdown, a phenomenon some theorists controversially attribute to quantum processes lingering in the vacuum's embrace. What makes this debate so electrifying isn't just the science, it's the stakes. If even a sliver of these ideas holds truth, it could redefine what it means to think to be asterisk. Could the vacuum act as a hidden bridge between mind and matter? Or is this just a modern echo of old dualist dilemmas draped in quantum buzzwords? For now, the theories remain on the fringe, neither proven nor dismissed, but they challenge us to ask, in a universe where emptiness teems with activity, where do we fit in? The answer, if it exists, might lie somewhere between the neurons in our skulls and the quantum static humming beneath reality itself. Mystery 28. The vacuum in extra dimensions for centuries. We've lived under the assumption that space has 3 dimensions: length, width, and height, with time as the 4th. But what if reality is far roomier than we ever imagined? String theory, one of the most ambitious frameworks in physics, suggests the universe might actually be hiding extra dimensions tiny, curled up spaces woven into the fabric of reality. And if they exist, they could rewrite everything we know about the quantum vacuum. Picture a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line. But zoom in close, and you'll see its surface wraps around in a second dimension, a hidden loop you couldn't perceive from afar. String theory proposes that space-time itself could have similar microscopic coils, additional dimensions so small they escape our notice. The catch, these extra folds wouldn't just sit quietly, they'd dramatically reshape how fields and particles interact within the vacuum. Here's where it gets mind-bending. If extra dimensions exist, the quantum vacuum's fluctuations wouldn't just ripple through the 3 dimensions we see, they'd propagate through all dimensions, altering the fundamental forces in ways we can't yet predict. Gravity, for example, feels mysteriously weak compared to other forces. Some theories suggest it might actually be leaking into these hidden dimensions, diluting its strength in our observable universe. The question is, how do we test something so abstract? The answer might lie in the world's most powerful particle smashers. Experiments at the Large Hadron Collider hunt for anomalies, tiny deviations in particle behavior that could signal interactions with unseen dimensions. If certain particles suddenly vanish or gain unexpected energy, it might mean they briefly tunneled into these extra folds of space before snapping back. Other proposals involve searching for microscopic black holes, another potential byproduct of higher dimensional physics that could wink in and out of existence within the vacuum's turbulence. Of course, skeptics argue that extra dimensions remain purely hypothetical, a mathematical convenience without hard proof, yet the implications are too tantalizing to ignore. If confirmed, they'd revolutionize our understanding of the vacuum's structure, dark energy, even the birth of the universe itself. The quantum vacuum might not just be a seething foam in 3 dimensions. It could be a sprawling, multidimensional labyrinth, whispering clues to a reality far stranger than we've dared to dream. So while we haven't yet glimpsed these hidden layers of existence, the search continues, one high-energy collision at a time. And if the universe is hiding extra pockets of space, they're not just empty rooms. They're part of the vacuum's deepest, most cryptic blueprint. Mystery 29. The vacuum's ultimate fate. The universe hums with motion, galaxies spin, stars burn, particles collide. But beneath all that activity lies an unsettling question. How does this all end? The answer might not lie in cosmic collisions or dying stars, but in the silent, shifting nature of the quantum vacuum itself. From the slow fade of heat death to the explosive rewrite of vacuum decay, the void could hold the blueprint for reality's final act. Let's start with the most sedate and likely scenario, heat death. In this future, the universe keeps expanding until every star burns out, every black hole evaporates, and all matter is reduced to a thin, cold haze of particles drifting endlessly apart. The vacuum would stretch into near-perfect stillness, its fluctuations still flickering but with no structure left to influence. Space wouldn't tear or collapse, it would simply forget, like a clock winding down with no one left to hear it tick. But heat death isn't the only possibility. Remember vacuum decay. That tiny quantum fluctuation could, in theory, rewrite physics in an instant. If our vacuum is metastable, balanced on a knife's edge, a single random event might trigger a catastrophic phase transition. A bubble of true vacuum could erupt somewhere in the cosmos, expanding at light speed and rewriting the laws of nature as it goes. Forces might reconfigure, particles dissolve, and fundamental constants shift overnight. Unlike heat death slow fade, this would be a cosmic Control-Alt-Delete abrupt and irreversible. Then there's the more optimistic twist, cyclic universes ***. Some theories suggest the vacuum might not be a one-way street. Instead of vanishing into darkness or collapsing into a crunch, our universe could rebound, a big bang birthing from the ashes of the old. String theory even proposes higher dimensional brains colliding in eternity, sparking new universes like flint striking steel. In these models, the vacuum isn't a tomb, it's a cosmic chrysalis endlessly recycling itself into fresh beginnings. So which will it be, freeze, shatter, or rebirth? The truth is we don't know, and that uncertainty is precisely what makes the vacuum's role so mesmerizing. It's the silent variable in cosmology's ultimate equation, a force that could quietly unmake reality or set the stage for a cosmos we can't yet imagine. One thing's certain, the void is anything but passive. Whether it cradles eternity's embers or lights the fuse for a new creation, the final chapter of the universe won't be written in the vacuum, it'll be written by it. And that leaves us with one final mystery, one last secret the quantum vacuum might yet reveal. Mystery 30. Measuring nothing How do you measure nothing It sounds like a riddle, but for physicists, it's one of the most urgent challenges in modern science. The quantum vacuum might appear empty, but as we've seen, it's a hive of invisible activity, and unlocking its secrets demands tools as ingenious as the phenomena they're designed to detect. From lab benches to deep space telescopes, researchers have turned the void itself into a laboratory, probing its mysteries with methods so precise they border on the surreal. Take the Hubble laser. By bouncing light between ultra-reflective mirrors in a vacuum chamber, scientists can eavesdrop on the faintest whispers of quantum fluctuations. Every so often, those fluctuations nudge the mirrors, an effect so minuscule it's like spotting a grain of sand shifting on the moon from Earth. Yet devices like LIGO, the gravitational wave detector, now spot movements 10,000 times smaller than an atomic nucleus, revealing how spacetime itself trembles under the vacuum's influence. Then there's cosmology's grand stage, when astronomers map the cosmic microwave background, the afterglow of the Big Bang. They're indirectly studying the quantum vacuum's fingerprints from nearly 14 billion years ago. Those faint temperature variations, they're the amplified echoes of primordial quantum jitters, stretched across the cosmos by inflation. It's as if the universe left us a fossilized recording of its own chaotic infancy, etched in microwaves. But the real frontier lies in the extremes. Particle colliders like the Large Hadron Collider recreate conditions so energetic, they momentarily peel back the vacuum's veneer, exposing strange behaviors like quark-gluon plasma a state of matter thought to have existed just microseconds after the Big Bang. Meanwhile, tabletop experiments with supercooled atoms or superconducting circuits tease out the vacuum's subtler quirks, like how it warps electron behavior or spawns fleeting magnetic fields. What's stunning isn't just the diversity of these approaches, it's their sheer audacity. To study nothingness, we've built machines that chill matter to within a whisper of absolute zero, hurled particles at near light speeds, and trained telescopes on the edge of observable time. Each method peels back another layer of the vacuum's paradox, that the emptiest places in existence are also the busiest, humming with secrets that redefine everything. So the next time someone dismisses nothing as uninteresting, remember, it's the most carefully measured, obsessively studied nothing in science, and its revelations are only beginning. Conclusion. The void speaks, and we're just beginning to listen. Over 30 mysteries. We've ventured into the quantum vacuum, not as passive observers, but as cosmic detectives piecing together a puzzle. Defies intuition. Every question answered seems to unveil 10 more, and that's the beauty of it. The void we once called empty is anything but. It's a dynamic, shimmering arena where particles blink in and out of existence, where space-time itself churns like a restless sea, and where the fate of the universe might hinge on secrets hidden in plain sight. From the Casimir Effect's invisible forces to the haunting possibility of vacuum decay, from entangled particles whispering across galaxies to the holographic principle rewriting reality's rules, we've seen how nothingness shapes everything. The quantum vacuum isn't just the backdrop of the cosmos, it's the architect, the sculptor, even the storyteller. And while we've uncovered staggering truths, the most thrilling realization is this: we're still scratching the surface. What's next? Maybe a lab will finally detect the Unruh Effect, or a telescope catch the first glimpse of extra dimensions. Perhaps a maverick experiment will tap into zero-point energy, or a quantum computer will reveal vacuum fluctuations in ways we never anticipated. The future of physics isn't just about building bigger machines, it's about learning to ask better questions. So here's to the void and to the curious minds daring to explore it. Which of these 30 mysteries fascinates you most? Drop your thoughts in the comments. Let's keep the conversation rippling through the quantum foam. And remember, the universe's greatest secrets often hide in the places we least expect. Stay hungry, stay questioning, and above all, stay amazed. Until next time, keep looking deeper. Because the nothingness, it's got a lot to say.